Imagine holding the entire mass of our sun. Picture its immense energy, its blinding light, and its overwhelming gravitational pull. Not in your hand, of course, because that would be impossible, but compressed into a sphere the size of a city. Yes, a city. Think about the bustling streets, the towering buildings, and the sprawling parks all fitting into this tiny, dense sphere. This, my friends, is the mind-boggling reality of a neutron star, a celestial object so dense that it defies our understanding of matter and space. These celestial objects are not just dense, they are the universe's ultimate heavyweights. Imagine something so heavy that a single teaspoon of its material would weigh billions of tons on Earth. But their story is about more than just extreme density. It's about the incredible forces at play in the universe. It's a story that takes us to the very heart of gravity, space, and time. These neutron stars challenge our understanding of the cosmos. It's a story that makes us question what we think we know about the universe. How can something so small have such a profound impact? What if I told you that even a tiny neutron, a particle so small that it is almost beyond our comprehension, a particle smaller than an atom, can warp the fabric of space itself? This tiny particle holds the key to understanding the universe's most extreme phenomena. It sounds like science fiction, but it's a profound truth revealed by the universe's most extreme objects. These neutron stars are not just scientific curiosities, they are windows into the fundamental nature of reality. It's a journey into the unknown, where the rules of physics as we know them are pushed to their limits. Join me as we delve into the mind-blowing world of neutron stars. Together, we will explore their mysteries, their incredible power, and their role in the grand tapestry of the cosmos, and unravel the mysteries of how something so small can have such a powerful effect on the cosmos. This is a journey that will change the way you see the universe. Before we plunge into the heart of a neutron star, we need to understand the stage on which this cosmic drama unfolds: space-time. Space-time is the very fabric of our universe, a four-dimensional continuum that combines the three dimensions of space with the dimension of time. It's a concept that was revolutionized by Albert Einstein's theory of general relativity. Imagine a trampoline, a taut fabric stretched across a frame. This simple analogy helps us visualize the complex nature of space-time. This, my friends, is a simple way to picture the fabric of space-time. Just as the trampoline fabric can be stretched and deformed, so too can space-time be warped and curved by the presence of mass and energy. Now place a bowling ball in the center. This represents a massive object like a planet or a star. What happens? The ball creates a dip, a curvature in the fabric. This dip is analogous to the way massive objects curve space-time around them. That, in essence, is gravity. Gravity is not just a force pulling objects together, it's the result of the curvature of space-time caused by mass. Objects with mass, like our bowling ball or a giant star, warp the fabric of space-time around them. The greater the mass, the more pronounced the curvature. This warping is what we experience as gravity. It's why we feel the pull of the Earth beneath our feet and why planets orbit stars. The more massive the object, the deeper the curvature, the stronger its gravitational pull. A small object creates a slight dip, while a massive star creates a deep well. Earth, the sun, even you and I, we all create our own tiny dips in this cosmic fabric. These dips are usually imperceptible, but they are there, influencing the space-time around us. But neutron stars? They take this curvature to a whole new level. With their immense density and mass, neutron stars create some of the most extreme warps in space-time, leading to gravitational forces that are almost unimaginable. This is the stage upon which the incredible phenomena of neutron stars play out, a stage defined by the very fabric of the universe itself. We've all heard the story: Newton, an apple, a flash of insight, gravity, the force that pulls the apple down, right? Well, not exactly. You see, gravity isn't just a force pulling things down. It's about objects following the curves in space-time. Imagine rolling a marble across our trampoline. It wouldn't travel in a straight line but would curve towards the bowling ball, following the contours of the warped fabric. That's how gravity really works. Planets don't orbit stars because they're pulled by an invisible string. They're simply following the curves in space-time created by the star's mass. It's a cosmic dance, a ballet of objects moving through a warped and wonderful universe. Now, imagine a star much more massive than our sun, reaching the end of its life. This star has burned through its nuclear fuel, and the balance between gravity pulling in and pressure pushing out is lost. It collapses under its own gravity, the core squeezed tighter and tighter until, boom! The core's collapse is so intense that it triggers a cataclysmic event. A supernova explodes, blasting the star's outer layers into space. This explosion is one of the most powerful events in the universe, outshining entire galaxies for a brief moment. Left behind is a core so dense that atoms themselves are crushed. The core, now devoid of its outer layers, is a remnant of unimaginable density. Protons and electrons are forced to merge, creating an object composed almost entirely of neutrons. This process is called neutronization, and it results in a core that is incredibly compact. This, my friends, is the birth of a neutron star, a stellar remnant that is both fascinating and mysterious. Squeezed into a sphere just a few miles across, it contains more mass than our sun. Imagine all that mass packed into a space the size of a city. A teaspoonful of neutron star material would weigh billions of tons on Earth. This incredible density is almost beyond human comprehension. But the story doesn't end there. Neutron stars can evolve in fascinating ways, sometimes merging with other neutron stars or black holes, creating even more spectacular cosmic events. This incredible density has a profound effect on the fabric of space-time. The gravitational pull of a neutron star is so strong that it warps space-time around it, creating phenomena like gravitational waves. Some neutron stars become pulsars, emitting beams of radiation as they spin rapidly. These beams sweep across space like cosmic lighthouses, providing us with valuable information about the universe. In binary systems, neutron stars can accrete matter from a companion star, leading to intense X-ray emissions. These interactions offer a glimpse into the extreme physics governing these celestial objects. Over time, the fate of a neutron star can vary. Some may eventually collapse further into black holes, while others may remain as neutron stars for billions of years, continuing to intrigue and inspire astronomers. Remember our trampoline analogy? Now, imagine replacing the bowling ball with something much denser, say, a small car compressed to the size of a pinhead. That's the kind of extreme gravity we're talking about with a neutron star. It creates a much deeper, more pronounced curvature in the fabric of space-time. Light, which normally travels in straight lines, is also affected. It bends as it passes close to a neutron star, following the curved space-time. This bending of light, known as gravitational lensing, is one of the most dramatic demonstrations of Einstein's theory of general relativity. We don't just have to imagine this cosmic distortion, we can actually observe it. The Hubble Space Telescope, our eye on the universe, has captured stunning images of gravitational lensing. Distant galaxies, their light warped by the gravity of massive objects like neutron stars, appear distorted, stretched, even multiplied in the telescope's images. These images are not just beautiful, they're powerful confirmation of Einstein's theories. They show us that even the tiniest particles, when packed together with the unimaginable density of a neutron star, can warp the fabric of the universe. So, can a single neutron bend space? The answer, surprisingly, is yes. A single neutron on its own has a gravitational effect so minuscule it's practically immeasurable. But in the heart of a neutron star, trillions upon trillions of these tiny particles combine their gravitational might. Together they create an object so dense, so massive, that it becomes a cosmic sculptor, warping space-time and shaping the universe around it. Neutron stars are a testament to the incredible power of gravity, a force that governs the motion of planets, stars, and even light itself. They remind us that the universe is full of surprises, of phenomena that challenge our understanding and push the boundaries of human knowledge. The study of neutron stars is just one window into the vast and mysterious universe we inhabit. As we delve deeper into the cosmos, we're bound to encounter even more mind-boggling phenomena, objects and forces that challenge our imagination and redefine what we think is possible. So the next time you look up at the night sky, remember the incredible story of neutron stars. Remember that even the smallest things can have a profound impact on the universe around them. And never stop asking questions, for the universe is full of wonders waiting to be discovered. What other secrets do these cosmic crushers hold? The quest for knowledge continues.